Let us review fundamentals of fluid flow in this particular lecture. So, the objectives of this lesson are to present equations for conservation of mass, conservation of momentum, and discuss Bernoulli equation and its applications, and discuss methods for evaluating friction pressure drop and minor losses. At the end of this lesson, you should be able to state laws of conservation of mass and momentum, apply these laws to fluid flow problems in refrigeration and air conditioning, and state Bernoulli equation and apply it to simple problems, and finally evaluate friction pressure drops and minor losses using suitable correlations and design data. Now, why do we have to study about fluid flow in refrigeration and air conditioning? As you have probably seen, in a typical refrigerant system or an air conditioning system, we will be handling a large number of fluids, for example refrigerants, air, water, etc. These fluids will be flowing from one point to the other. That means fluid flow is involved in all these systems. Now, these fluid flows are subjected to certain fundamental laws of fluid mechanics. So, in order to understand or in order to design refrigeration and air conditioning systems, one must know the fundamentals of fluid mechanics or fluid flow. Okay. So, that is what is mentioned here. In refrigeration and air conditioning systems, various fluids such as air, water and refrigerants flow through pipes and ducts, and the flow of these fluids is subjected to certain fundamental laws, and the subject of fluid mechanics deals with this subject with these aspects. Probably you have studied the fluid mechanics, so it is not possible to review the entire subject here, but we will be presenting the basics of these things relevant to refrigeration and air conditioning. Now, fluid flow in general can be compressible or incompressible. What do we mean by compressible flow? A compressible flow means the density of the fluid varies along the flow direction. That means basically fluid density varies as the fluid flows. So such flows are known as compressible flows. And in incompressible flow, the density remains constant, it does not vary. In most of the refrigeration and air conditioning applications, the fluid flows can be assumed to be compressible. Why do we assume this? Because this will simplify the problem considerably. So, most of the times we assume the flow to be incompressible and the resulting mathematics will be simpler. However, you cannot just like that apply the assumption of incompressible flow everywhere. You have to see its validity. The assumption that the flow is incompressible is valid as long as the velocity of fluid is much smaller than the local sonic velocity. That means the velocity of the fluid should be smaller than the velocity of sound, or in other words the Mach number should be less than 0.3, and as you know the Mach number is the ratio of velocity of fluid divided by the sonic velocity. So, when the Mach number is less than 0.3, you can assume the flow to be incompressible and apply the suitable laws. Now, to analyze fluid flow problems, one has to consider three conservative equations. They are equations for conservation of mass, equation for conservation of momentum, and equation for conservation of energy. Conservation of energy is nothing but your first law of thermodynamics, which we have discussed in the review on thermodynamics. So, in this present lecture we will be discussing conservation of mass and conservation of momentum. Now, depending upon the approach, you can write these equations either in integral form or in differential form. That means, if you are taking a control volume and apply these conservative laws, you get integral form of equations, or if you take a differential element inside the control volume and apply the conservative laws, you get the governing equations in differential form. In the present lesson, I will just give you only the integral forms of conservation of mass and conservation of momentum. Now, this equation shows the conservation of mass. As the name implies, conservation of mass in simple terms is that mass can be neither created nor destroyed. Just like energy, you cannot create mass nor you can destroy mass. So, if you apply this conservation of mass to a control volume, then you get a equation of this form. As you can see in this equation, you have two terms. The first term here is Okay. So the first term here, I am sorry, is the rate at which the mass of the control volume is varying with time. That means time rate of change of mass of the control volume. CV stands here for control volume. And the second term is nothing but the net mass flux out of the control volume. So the conservation of mass when applied to a control volume gives you two terms, two integral terms, since you are applying integral form. So this first term accounts for the rate at which the mass of the control volume is varying with time, and the second term accounts for the net mass flux out of the control volume. In this equation, rho is the density, t is the time, and v is the velocity vector with reference to the control volume. Okay, and when the flow is steady, that means when the flow does not vary with time, this term will not be there. So this equation boils down to conservation of mass for a steady flow situation. So these equations are also known as continuity equations. So basically for steady flows we will be having this kind of an equation. Now if you apply this conservation of mass to a one dimensional steady flow through a duct, let us say that we take an arbitrarily shaped duct, and let us say that this is the control volume, and let the flow be steady and the flow be one dimensional. Since the flow is steady, no mass can be accumulated within the control volume. That means the mass inside the control volume is constant. That means whatever mass is entering, that must leave the control volume. Okay, that is what is written here. The rate at which mass is entering into the control volume is equal to the rate at which mass is leaving the control volume, and the rate at which mass is entering the control volume can be written as a product of density rho 1, cross sectional area A1 at the inlet, and velocity V1 at the inlet. Similarly, at the outlet you can write the mass flow rate out of the control volume as rho 2 into A2 into V2. Oh, so this is the simple one dimensional steady flow equation when you apply it to any duct. Now if the density is constant, that means when rho 1 is rho 2 is rho, then you get a conservation of mass in a very simple form as A1 V1 is equal to A2 V2. Okay. Right. So for steady incompressible flow for a one dimensional situation, we get the conservation of mass equation as A1 V1 is equal to A2 V2. Now when A1 is greater than A2, then the velocity V1 should be less than V2. This is what is known as a nozzle. That means the velocity increases in the direction of flow as the cross sectional area reduces in the direction of flow. This is what is known as nozzle. And when the reverse case, when A1 is less than A2, that means cross sectional area increases in the direction of flow, then obviously according to the conservation of mass equation, the velocity should reduce in the direction of flow, and this is what is known as a diffuser. Now let us look at the conservation of linear momentum. This is nothing but a mathematical expression for Newton's second law applied to a control volume, and the general equation in integral form is like this. So here what we have is dp by dt applied over a control volume. This term is nothing but rate of change of linear momentum of the control volume, and this is equal to, according to Newton's second law, is a net force acting on the control volume. This is nothing but the Newton's second law, and when we apply this to a control volume, we can write this and introduce two terms. You have one term here, another term here. This first term accounts for the rate at which the momentum of the control volume is increasing with time. So this term accounts for the rate of change of momentum of the control volume, and the second term accounts for the net momentum flux out of the control volume. So in simple terms, the conservation of linear momentum says that the net force acting on a system is equal to sum of the rate at which the momentum of the control volume is increasing plus net momentum flux out of the control volume. This is a vector equation. That means you can write this equation for different directions. For example, you can have linear momentum equation for x direction, linear momentum equation for y direction and z direction. So this can be written in this form. The net force acting on the control volume can be split into sigma fs plus sigma Fb, where this is the sum total of all the surface forces and this is the sum total of all body forces acting on the control volume. So finally the linear momentum equation boils down to sigma Fs plus sigma Fb is equal to the momentum rate of momentum change of the control volume plus net momentum flux out of the control volume. Now for steady state, again just like conservation of mass, for steady state you don't have the time terms. So the linear momentum equation for steady state becomes like this, where Fs stands for the surface forces acting on the control surface and Fb accounts for all the body forces acting on the control volume. So the sum of these two forces is equal to net momentum flux out of the control volume. And what are the typical surface forces? The typical surface forces are pressure forces, forces exerted by the physical boundary on the control surface, etc. Okay, and the most common body force is the gravity force acting on the mass inside the control volume. Now some of the applications of linear momentum equation are force exerted by the fluid flow on nozzles, bends in a pipe, etc. That means we want to find out what is the force exerted due to fluid flow on nozzles and on the walls of the pipe and the bends, etc. Then you have to apply the linear momentum equation, and linear momentum equation is also applied to find the motion of rockets and the calculation of motion of rockets, and it's also applied for in water hammers, etc. Now let me give an example of the application of linear momentum equation. This is a very simple example. What we have here, okay, let me read the problem. We have here a straight rigid 100-meter long pipe through which water flows. Okay, so water flows through this pipe and it has a diameter of 0.25 meter. Okay, so diameter of the pipe is 0.25 meter. It is rigid, it is horizontal, and it's 100-meter long. And the water enters at certain pressure and it leaves at a pressure that is equal to atmospheric pressure. That means here you have P2 is equal to 1 atmosphere. So basically the pipe discharges water into atmospheric pressure, and at a given instant the flow rate is 0.01 meter cube per second. That means the flow rate of water through the pipe at a given instant is 0.01 meter cube per second, but it increases at a rate of 0.1 meter cube per second square. That means the flow rate through the pipe is not constant, but it increases with time, and the rate at which the flow rate is increasing is equal to 0.1 meter cube per second. And we can assume the water to be incompressible, and we can also neglect frictional effects and take the density of water as 100 kg meter cube. And what we have to find out is what should be the pressure at the inlet so that water under these conditions can flow through this pipe. So first what we do is we apply the conservation of mass. Even though here the flow is not steady, since we have a rigid pipe, a rigid horizontal pipe, and the water is incompressible, the mass of the control volume cannot change because the volume of the control volume is constant. So the amount of mass within the control volume is constant at any given instant. So it doesn't change with time. That means whatever mass enters into the control volume must leave the control volume. Okay, so if you apply this, then you get the conservation of mass equation as A1 V1 is equal to A2 V2. That means and since the area is constant at every place, if it's a uniform cross section pipe, the velocity remains constant throughout the pipe. So this is basically the conservation of mass. Now let us apply conservation of linear momentum. As I have already shown, conservation of linear momentum says that the net force acting on the control volume, so this is the control volume here, I have shown the control volume by dashed line. The net force acting on the control volume consists of the sum total of all surface forces plus sum total of all body forces, and this is equal to the rate at which the momentum of the control volume is increasing plus net momentum flux out of the control volume. That means this term is nothing but at any given instant what is the difference between the momentum out of the control volume minus momentum entering into the control volume. That means momentum at this point minus momentum at this point. Now the mass flow rate is constant at any given instant, and the velocity at this point is same as velocity at this point. So their net momentum flux out of the control volume is 0. That means this term is 0 for this particular problem. And since we are neglecting frictional effects, and if since the pipe is also horizontal, there are no body forces also, so this term is also not there. Then the surface forces in x direction is simply because of the pressure difference at the inlet and the outlet. That means sigma Fsx is nothing but P1A minus P2A, that is equal to A into P1 minus P2, which is equal to pi d square by 4 into P1 minus P2. So this is the net force acting on the control volume in the x direction. So this should be equal to the rate at which the momentum of the control volume is changing. So the rate at which momentum of the control volume is changing is this, and here the small v is the momentum per unit area, okay, which momentum per unit area, and this can also be written as, it is some kind of velocity, and this can be written as volumetric flow rate divided by the cross sectional area. That means v is equal to q by a. So if you substitute q by a for v, you get this equation, and if you integrate it over the entire volume, this dv is the differential volume, and the total volume of the pipe is equal to L into A. So this equation becomes d by dt q by a into rho La, and A get cancelled. So ultimately you have rho L dq by dt, and in the problem it is given that dq by dt is 0.1 meter cube per second, and rho is given as 100 kg per meter cube, and length is 1 meter. So if you substitute this these values here and then use the equations 1 to 4, you get the answer P1 is equal to 304.7 kilopascal absolute. That means the pressure here should be 304.7 kilopascal, so that the flow can take place. This is a very simple application of linear momentum to a pipe flow, and the same linear momentum principle is used in many other applications, and when we discuss the fluid flow aspects through refrigerant pipes and ducts, we will discuss these issues. Now, similar to linear momentum, we can also write a conservative equation for moment of momentum or angular momentum. This equation is known as moment of momentum equation, and this states that the net moment applied to a system is equal to the rate of change of angular momentum of the system. This is known as the conservation of angular momentum, and this is very widely used in hydraulic machines such as pumps, turbines, centrifugal compressors, etc. Now let us look at one of the very important equations called Bernoulli's equation. This equation is applied in a wide variety of fluid flow related problems, and in it can be derived either from the momentum equation or from the first law of thermodynamics. That means either you can use the momentum equation or basically the Euler's equation, or you can also derive the same equation from first law of thermodynamics or conservation of energy equation. And this equation in simple terms relates pressure, velocity and elevation along a streamline, or pressure, velocity and elevation between any 2 points in the flow field. Now I am sure that you have studied about streamlines in fluid mechanics, but let me just give the definition of streamlines. Streamlines are the lines drawn through the flow field in such a manner that the velocity vector of the fluid at each and every point on the streamline is tangent to the streamline at that instant. That means streamlines are lines drawn through the flow field. If you take a point on the streamline and draw a tangent, that gives the direction of the velocity of the fluid at that point. So this is the basic definition of a streamline. Now the concept of streamline is very useful in describing a flow field in terms of speed and direction of flow. If you want to describe a flow field, as you know that it is a vector field, you have to specify both the magnitude and direction. So the concept of streamline is very useful for such flow field description, and it can be shown from continuity equation that when the streamlines are very close to each other, that means the speed of flow is high. That means, or in other words, speed of flow is inversely proportional to the spacing between streamlines. Now Bernoulli equation is applicable along a streamline under the assumptions of steady flow, one dimensional flow, incompressible flow and inviscid flow. So what do we mean by steady flow? As you know, steady flow means the flow doesn't vary with time. So whenever you have fluid flow situations which do not vary with time, you call that flow as steady flow. And what do we mean by one dimensional flow? One dimensional flow means properties vary only in one dimension. They are in the other two dimensions they remain constant. That means at any cross section the fluid properties remain constant. If you are talking about one dimensional flow in x direction, that means in y and z direction there are no variations in the fluid properties at any x. So, this is the meaning